Hello, everyone. I'm really excited to talk about our new work that solves a very important open problem in the theory of auction design, or specifically in the theory of combinatorial auctions. Let us start by defining combinatorial auctions. In this talk, we shall only be concerned with two-bidder combinatorial auctions, where there are two bidders, Alice and Bob, and a certain set of items that they want to purchase. The bidders, Alice and Bob, have valuation functions, V1 and V2, that are defined on subsets of items and determine the value they get from that subset. For example, if S here is a subset of items, then V1 of S will be the value Alice gets when she receives the set S of items, and V2 of S will be the value Bob gets when he receives the set S of items. The bidders have these valuation functions, and using these valuation functions, they interact with the auctioneer. And as a result of this interaction, the auctioneer is able to compute an allocation, which is a set S1 of items that he will give to Alice, and a disjoint set S2 of items that he will give to Bob. Due to this allocation, Alice will receive value V1 of S1, while Bob will receive value V2 of S2. And the goal of the auctioneer is to maximize the sum of these two values, also known as the welfare. The auctioneer actually wants to maximize this welfare while minimizing the amount of communication that happened during the auction. And his goal is, again, to maximize welfare while minimizing communication. What is the goal of the bidders? It turns out that there are two different regimes in which combinatorial auctions are studied. And the goal of the bidders is different in both these regimes. The first regime, that is called a non-truthful auction, is such that the goal of the bidders is the same as the goal of the auctioneer. And all the three parties in our system work together to maximize the welfare. In the other regime, called truthful auctions, the goal of the bidders may be different from the goal of the auctioneer. And in this regime, the auctioneer actually has to work harder and make the bidders maximize welfare along with him. So clearly, the task of the auctioneer is at least as hard in a truthful auction than it is in a non-truthful auction. And the main question that we study in this paper is whether it is strictly harder. In other words, we want to know whether there is a setting of combinatorial auctions where the amount of communication needed for a truthful auction is strictly higher than the amount needed for a non-truthful auction. As a standard, we shall ignore polynomial factors, and we only want to find out whether there are settings where truthful auctions require exponentially more communication than non-truthful auctions. This question is not new and is actually at the very core of auction design and has been studied since many years. In fact, the answer to this question is known in very many simple cases, such as the case of exact welfare maximization. In this case, the auctioneer actually wants to output an allocation, which is two sets, S1 and S2, that maximizes the welfare exactly. And it turns out that for this exact welfare maximization case, truthfulness only needs a polynomial overhead as compared to non-truthful auctions. That is, the amount of communication needed to run a truthful auction is only a polynomial more than the amount of communication needed to run a non-truthful auction. The reason why I'm calling it a simple case is because in most settings of interest, you do not consider exact welfare maximization. On the other hand, what you do consider is approximate welfare maximization. And in this approximation case, the question that we are interested in is the following. Are there truthful auctions with strictly lower approximation guarantees than non-truthful auctions? And of course, we're only dealing with polynomial communication. This question is much harder, and it's actually wide open. On the one hand, we know settings where the approximation guarantees given by non-truthful auctions match those that are given by truthful auctions, so there is no separation. While on the other hand, there are settings where there's a large gap between the approximation guarantees given by non-truthful auctions and the best known approximations that truthful auctions can give. One such setting is the setting of XOS, where both the bidders have valuation functions from the class XOS. I will not define this class formally, but all we need is that for XOS valuations, there is a non-truthful auction that guarantees welfare within 3/4 of the optimal value. Furthermore, we also know that 3/4 is the best possible guarantee, and no non-truthful auction can provide a better one. This means that the best possible approximation ratio for XOS valuations and non-truthful auctions is exactly 3/4. For truthful auctions, on the other hand, all we know is that the ratio lies in this interval, which is 1/2 to 3/4. Observe here that if we could shrink this interval even a little bit, if we can show that this approximation ratio for truthful auctions is bounded strictly away from 3/4, then that would imply a separation between the ratio you can get from truthful auctions and the one you can get from non-truthful auctions. And indeed, this is our main result. We show that when the valuation functions of the bidders are from the class XOS, then the best approximation guarantee that any truthful auction that has polynomial communication can provide is strictly lower than 3/4. And this implies a separation between the power of truthful and non-truthful auctions. I emphasize here that this is the first such separation. And even though we work only with XOS valuation functions, you can consider settings with different valuation functions. You can consider a setting where the valuation functions are submodular. You can consider a setting where the valuation functions are subadditive, where you can consider settings where they are monotone and like general valuations. We only work with 2 bidders, but you consider 3 bidders, you consider 4 bidders. You should also consider n bidders. Regardless of the setting you consider, our result is actually the first separation between truthful and non-truthful auctions in that setting. And so it's really special. This was the main result. And in the rest of this talk, I will cover the ideas that go behind this result. I'll start by describing at a very high level the steps in the proof. And then I will narrow down to the main idea, and I will illustrate this idea on a toy example. So let's start. We want to get here. We want to get a guarantee that no truthful auctions can have approximation more than 3/4. And the first step in our proof is to use a result by Shahar Dobzhinsky from 2016, where he shows that in order to get this, in order to get that the best approximation guarantee for a truthful auction is less than 3/4, all you need to show is that the best approximation guarantee for a non-truthful auction that is also simultaneous is less than 3/4. What is a simultaneous auction? Well, a simultaneous auction is just a regular auction, but it has a special structure. In a simultaneous auction, the 2 bidders, Alice and Bob, are restricted to only send one message to the auctioneer, after which the auctioneer must output the allocation. So again, you have Alice and Bob with valuation functions. They use these valuation functions to compute exactly one message. The auctioneer gets these messages, and using these messages, he outputs an allocation, which is a S1 set for Alice and a set S2 for Bob. And this is a simultaneous auction. Okay, so Shahar Dobzhinsky tells us that if we get a lower bound, if we can show that the approximation guarantee that a simultaneous auction can provide is less than 3/4, then we automatically get that the approximation guarantee that a truthful auction can provide is also less than 3/4. So how do we show this? How do we show that simultaneous auctions cannot have guarantees better than 3/4? Well, another major step in our proof is to use the result of BMW, where they do show a bound of 3/4 for simultaneous auctions, but it's for a slightly different problem, but related problem. What BMW show is that the decision problem for simultaneous non-truthful auctions is hard to approximate within a factor of 3/4. What is the decision problem? The decision problem looks exactly like a regular auction, but this time the auctioneer only needs to output one bit low or high. So the bidders again have valuation functions. It is again simultaneous, so they send one message to the auctioneer. But instead of outputting 2 sets, one each for Alice and Bob, this time the auctioneer only needs to output low or high. He should output high if the optimal welfare that V1 and V2 can give is at least 1. And he should output low if the optimal welfare that V1 and V2 can give is at most 3/4. And when it's in between 3/4 and 1, he can output anything. So again, this is the decision problem where instead of outputting an allocation, the auctioneer only needs to output a bit, which says whether the optimal welfare is low or high. It turns out, and as BMW show, that the decision problem and the allocation problem are incomparable, and a result for one does not imply anything about the other. The main step in our proof is to go from the decision problem to the allocation problem. And we show that even though these two problems are incomparable, there is a way to translate two copies of the decision problem into one copy of the allocation problem that is also hard. So this is our main idea. We take two copies of the decision problem and we massage the system to somehow get one copy of the allocation problem and show that it is hard to get welfare that is 3/4 of the optimal on this one copy. Let's see how. So now you have two copies of the decision problem, which means two sets of items and two valuation functions for both the bidders. The valuation function U1 and U2 correspond to the first copy and are defined on the first set of items. And the valuation functions V1 and V2 correspond to the second copy and are defined on the second set of items. We will ensure that a uniformly random one of these copies is a high BMW instance, which just means it has a high welfare, more than one. And the other one is a low BMW instance, which means it has a low welfare of less than 3/4. And we want to show that the referee cannot output an allocation that guarantees welfare within 3/4 of the optimal. Let us first show this under a restriction. And the restriction would be that the referee can only give an allocation that is contained in one of the two copies. For example, the referee may output the following allocation S1 and S2, which is contained entirely in the second copy. The referee may also output an allocation that is contained entirely in the first copy, but our restriction says that he can never output an allocation that is contained partly in both of the two copies. Under this restriction, I claim that our result follows and the referee cannot output an allocation with high welfare. Why is that? Well, in order to output an allocation with high welfare, the referee needs to at least determine which one of the two copies has high welfare and output an allocation in that copy. However, by BMW, we get that determining which copies is high is hard, and therefore it is also hard for the referee to output an allocation with high welfare under this restriction. Okay, so now what remains to be done is to somehow remove this restriction and get the same result for a general combinatorial auction setting. I will not give the full details on this, but what I'll do instead is I will show this result under a different restriction. This new restriction will be simpler and it will actually be more implementable than the one we had before. I will not tell you how we implement this in an actual auction, but just leave it by saying that it is implementable. Okay, so now the two copies of the items have been merged to one copy, but the bidders still have two valuation functions. One of them is low, a random one, and the other one is high. And the restriction this time is that the bidders can only use one of their valuation functions in the auction. So, for example, Alice may want to use the valuation function V1 and Bob may want to use the valuation function V2 because they guarantee high welfare. And these will allow the auctioneer to give them an allocation that has high welfare. It may seem at first sight that a lower bound would still follow by the same argument. Alice and Bob do not know which one is the low valuation function and which one is the high valuation function. Therefore, they cannot decide which valuation function to use, and therefore they cannot get an allocation with high welfare. However, this reasoning is flawed due to the following example. Consider the case where Alice always wants to use the first valuation function, while Bob always wants to use the second valuation function. I claim that in this case, regardless of which one is the high valuation function, one of the two bidders is still using a high valuation function. And it turns out that this is sufficient for the auctioneer to get an allocation with high welfare. In fact, the problem is more serious. And it so happens that even if both of these pairs, the pair U1, U2 and the pair V1, V2 are low instances of BMW, you can still get cross terms, which are U1, V2 and V1, U2 that have high welfare. So you may have a picture that looks like this. You have U1 and U2, which is a low instance of BMW. You have V1 and V2, which is a high instance of BMW. But the cross terms that they generate, the term U1, V2 and the term U2, V1, both have high welfare. And this is problematic because this will allow an attack like the one we described. Alice will just use U1, Bob will just use, Alice will just use U1, Bob will just use V2, and they will have high welfare. So how do we get around this? And what exactly is this problem? In the rest of this talk, I will be focusing exclusively on how to handle these cross terms. And I'll do this under a simplifying assumption. I will assume that there are exactly 12 items, and the valuation functions of the bidders are defined by a subset of these 12 items. So for example, the valuation function U1 may be this subset of the first 6 items. And all this means is that the parties get some unit welfare when they get an item in this subset, and they don't get any value when they get an item outside this subset. Similarly, let's say Bob's valuation function is defined by this set 3 to 8 of the items. In this notation, the optimal welfare happens to be the size of the union of these sets. So for example, for our left pair, the optimal welfare will be the union, which is of size 8. 8 over 12 is 2 over 3. 2 over 3 is less than 3 over 4. And therefore, this is a low instance, as its optimal welfare is less than 3 over 4 of 12. Similarly, V1 and V2 may be another low instance that looks like the following. This time Alice has the set 7 to 12, Bob has 5 to 10, and again the union is of size 8, which is 5 to 12, and which corresponds to another low instance. Now, even though both of these instances are low instances, observe that the cross terms that they give have a large union and therefore a high welfare. For example, the cross term that this valuation gives with this valuation has a union of size 10. The union is all the items from 3 to 12. And 10 over 12 is more than 3/4. So this cross term has a high welfare. And similarly, this other cross term also has a high welfare. And these high welfare cross terms are exactly the problem that our original argument was facing. It may seem at first sight that this is because I chose the first 2 sets to be disjoint, and that somehow led to the cross terms being high, but that is not actually the case. The problem is more serious, and even if these sets were chosen randomly, the size of the cross terms would still be at least 3/4. And a lot of work needs to be done to get around this. How do we do this? Well, our solution is to ensure that the cross terms also have some structure. And the way we do this is that we will not allow this valuation pair on the left to combine with any random valuation pair on the right. Instead, we will only allow it to combine with this particular looking valuation, which still satisfies that the union is 8, so it's a low instance. I will not verify this. But additionally, now the cross terms also have union 8 and therefore are low instances. For example, this and this form a cross term with union 1 to 6 and 9 to 10, a total of 8 entries. Again, 8 over 12 is 2 over 3, which is less than 3/4. And therefore, this corresponds to a low instance. And similarly, the cross term formed by this of this have union 2 to 9, 3 and 8 are here, and 2 and 9 are here. Again, the size is 8, and therefore it's again a low instance. With this low instance, when the cross terms are low instances like this, our original argument can go through, and we are able to get a reduction. We're able to get a construction where it is hard to get an allocation that has welfare within 3/4 of the optimal. Okay, so I would like to conclude by saying some remarks on what remains to be done. Recall that in our original construction, one pair of valuations was a low BMW instance, and the other pair of valuations was a high BMW instance. But when I was talking about cross terms, I changed these valuations so that both of them are low cross terms, low valuations. How much do things change when one valuation is low and one valuation is high. Clearly, it's harder this time because now you also need to control terms that are inherently large. And this requires much more work. I will though omit the details about how we do this and next mention another property that follows from one of the copies being low and the other copy being high, which is that the optimal welfare is always high. And the reason I'm saying this is that because the optimal welfare is high, our construction is actually very easy for the decision problem, where the decision problem would simply say high all the time and be correct. This emphasizes the fact that the decision problem and the allocation problem are two very different problems, and different techniques are needed to tackle both of them. Okay. Lastly, I will end this with some open problems. The major open problem left open by this work is that what is the best approximation guarantee that a truthful auction with XOS valuations can provide? In this work, we did show that this guarantee is bounded strictly away from 3/4, but we did not find the exact constant. And finding this constant is a very interesting open problem. In fact, even determining whether this constant is strictly larger than half or exactly half is also interesting, because the truthful auction that guarantees a half approximation to the welfare is trivial. You just give all the items to one of the bidders at random. And we know that this is truthful and it guarantees an approximation ratio that is exactly half. So it is very interesting to find out if this trivial auction is the best you can hope for XOS valuations. It is so interesting that I'll stop speaking here and leave you thinking about this open problem. Thank you.